All right, 6:05. Get started. So welcome back. We're doing regression today. The group size is shrinking.
A lot of people are home. We don't have school tomorrow.
No school tomorrow?
There's a fast day, so they gave us off.
Oh, really? Oh.
Yeah.
What holidays tomorrow?
It's just a fast day. Like we can't eat or drink all day tomorrow. Yeah.
Okay.
It's not really a holiday. It's like a, I don't know. It's a commemoration day. Yeah.
I see. Okay. Well, make sure to drink enough.
It always is.
Make sure to drink enough water before you stay thirsty.
Okay.
Okay. So we're getting started today with regression. So regression is essentially a continuation of correlation. So we have spoken last time about correlation. I just want to quickly go back and do a quick recap on correlation. So make sure that the basic understanding is solid. So we have spoken last time about correlation. So first limitation, and this also applies to regression, is that correlation does not imply causation. And this is extremely important because in the light of big data becoming more prevalent, and you're likely going to use larger data sets than people may have used in the past, this is just to some extent important to keep in mind, because once you have a larger sample size, you're more likely to see correlation as well as associations that may not necessarily be true. We've spoken about the correlation coefficient, that essentially is a mark of the strength of an association ranging between -1 and 1. And this will become important today because it's not only reflecting the strength, but it also represents the direction, as we've talked about it yesterday, last time, Wednesday. Where a positive correlation essentially indicates that it's the increase of y with an increase in x, whereas a negative correlation does imply a decrease in y with an increase in x. So this becomes important with regression, because this to some extent also reflects the strength of an association in terms of its positioning within the coordinate system. When there's a strong correlation between two variables, this association will tightly resemble a 45-degree increase with between y and x. So with an increase in y, you have an increase in x. So this also kind of has a relationship with how that perfect fit line, the best fit, associates and presents in the coordinate system. And this becomes important today because today we're using the correlation coefficient to extrapolate it into a standardized regression, and by that basically estimate the slope of an association. So we have spoken about the sizes of correlation coefficient that are basically being judged based on its absolute value, where we have 3 different levels: small, medium, and large, with large being everything exceeding 0.5 of the correlation coefficient. We've talked about that the absolute value is the reflection of the strength and not its numerical value. We've spoken about misleading correlations, where you have to take into account third unknown or unquantified variables, where we spoke about ice cream eating and the association of drowning deaths. And we have spoken about directed acyclic graphs and to what extent you have to factor in third unknown variables to understand the relationship between exposure and outcome. Pearson correlation coefficient. We've talked about the calculation of this Pearson correlation coefficient, where we basically multiply the deviation of each individual x from the mean with the deviation of each individual y from the mean of y. this sum of products divided by the square root of the product of the sum of squares of x and y essentially allow us to quantify the correlation coefficient. This can be used in hypothesis testing, where the null hypothesis is essentially that the association is not present, and we're testing this against a flat line that in magnitude represents the mean of x or y. We've done this example with the missed classes and the relationship to statistic exam grades. Hopefully it's not going to be evident in this class when it estimates. So we always start with a scatter plot to always kind of map it out, look at the distribution of individual scores, and calculate the correlation coefficient based on the formula that we just discussed. Partial correlation, we talked about third variables that essentially reduce the amount attributed to one association only, where basically a third variable takes away from the correlation between two variables. This is in further education, in further statistics education, this becomes very important when thinking about mediating factors of third variables. We've talked about the correlation of psychometrics, talked about tests and measures, reliability and validity. Talked about test reliability and split half reliability, and the Kronberg alpha as a way to quantify the internal consistency of a test to basically find out whether the validity is given by quantifying split half correlations, whether these all point into the same direction of an outcome. Very important whenever you develop surveys, the Kronberg alpha. Validity is essentially the accuracy of an estimate based on your survey. And this essentially allows you to understand how well it is the test representing or reflecting what you actually want to measure. And and the doubt, the validity of personality quizzes, I leave that to the textbook, but yes, most personality quizzes are likely not very valid in the interpretations. So today was regression. We're moving further into the topic. So we do have a quiz on Wednesday. This quiz will cover correlation and regression, and also today's class. Essentially what we're doing today will be on the quiz as well. These two sample quizzes, they're quite central. Also have a look at the homework. The homework essentially will make you think a bit. So it's not trivial, but it's a fun exercise because it allows for you to see the value regression has in the real world. Yes, Amira.
So there's no quiz on Moodle? There's no quiz on Moodle?
No, but it will be on the final. It will be on the final. Yes.
Is it possible to have a quiz on Monday? Is the other one?
No, because on Monday we do chi-square. And on Wednesday is a lab day, which I'd rather sacrifice lab day time than lecture time.
Okay.
So the fasting is also on Wednesday now? Okay. So it's on Tuesday, but everybody's home, or what's the situation?
Some people are going, some people stay.
Yeah, that's I can't swap.
Study on draft day.
Yeah, it's a little complicated, but I can't deviate much with the quiz because chi-squared is going to keep us busy. Okay, regression builds on correlation. Are there any questions about correlation, just a principle?
Wait, this would be on correlation?
Correlation and regression. So Wednesdays and regression, yes. No and over. No and over. Yeah, you're off the hook until the beginning of January. Learn it for the final. Good. Okay. So correlation describes an association, right? And we've talked about this with the correlation and the strength, but it also shows in the context of the coordinate system, how does this correlation, how does this association present in terms of direction, but also in terms of the degree over the entire range of magnitudes of the parameters. So this is what regression builds on. Regression uses the correlation coefficient to essentially use it for prediction. And this is where regression becomes an extremely useful tool. And we've looked at it on that Excel spreadsheet where we depicted the scatter plot on Wednesday last week. And, so we looked into the regression function, which basically had a slope and had an intercept, and also had the R squared. So we will calculate all of this today. And yeah, so univariate or simple linear regression is a tool that predicts an individual score of y, of the dependent variable, using the independent variable on the x-axis, which means that you can have every arbitrary value of y that you want to predict. And this is true for a univariate regression. So univariate, so you will hear this term more often. You will hear univariate or multivariate or univariable, multivariable, same thing. Which basically is here used synonymously with simple linear regression. So this just means that there's one x that predicts one y. And yeah, so the definition is that regression is a simple linear regression. Univariate regression is a statistical tool used to predict an individual scores on the dependent variable using a score on one independent variable. Notably on one. Once you have a multivariable, you basically have additional covariates in your model that essentially allows for you to calculate it based on several characteristics. So there are models out there with like up to 200-300 variables that you can include. It takes an enormous amount of processing time, particularly with large data sets, because covariates you only can include with an adequate sample size. So there needs to be a relationship between sample size and covariates included. And this is the aforementioned standardized regression equation. So you have a standardized regression equation that builds a relationship between the set score of a dependent variable and the set score of independent variable x. And this will basically allow you to predict the set score of a y hat. And the y hat indicates that it's predicted variable. Remember, we had a y bar. Y bar means it's the mean of y. When you have a y hat, this little hat here on top of the y, that indicates it's a prediction. Right now, you will see it only in the context of regression, but you will see it in all further stochastic application. You will see it more often because you're predicting much more later on. So this set y hat is now calculated by using the correlation coefficient, which essentially gives you an idea about the direction of the association. It gives you an idea about the positioning of that equation, of that function, of that association, of the best fit line in the space of your coordinate system. So when you multiply your set x with your rxy, so your correlation coefficient multiplied with the set score of your x, of any arbitrary x that you want to do, you get a predicted y, set y. And with a set y, you can calculate your y hat, right? Or set y hat. So this knowledge is obviously very insightful and very powerful because now, so this is an example from the book. This is using a correlation coefficient of 0.58, which is somewhere in the example that we're going to do later on. I'll leave it to you to read that. But you basically see the multiplication of a set score with the predictor of the variable x. So that's set x multiplied by 0.58. So obviously you see that there's a relationship essentially between the sets x and set y hat. And this relationship we're building on by using it for the estimation of slope and intercept. Because we know that the intercept is where the function crosses the y-axis, where x equals 0. So that's the definition of the intercept. And now with the knowledge of the intercept, you can characterize this function easily by taking the intercept and also quantify the slope. And the slope is the increase of this regression function with each unit on the x-axis. So this is basically what you see here, right? So this is the prediction, and this prediction increases by a constant amount with each increase on the standardized x set x. And okay, so logically, when you think now about this, the correlation, the way we estimated the correlation coefficient, we have built the product between an individual x minus a mean of x multiplied by an individual y minus a mean of y. So this product essentially led us, after division of the square root of the product between sum of squares x and sum of square y, to get the correlation coefficient. So now arithmetically, there needs to be something, a tendency to move towards the mean. And this is what the regression of the mean says. So when you have extremely high values, these will be outliers. So these outliers are rather the exception. And overall, this entire function will always gravitate towards the mean. And the mean will essentially where it stabilizes and where it basically positions itself. Does that all make sense so far? Yeah? Thank you. Okay, so now all this being said, the mean is going to be your basis, and everything is going to gravitate towards the mean. So this function is gravitating towards the mean. And with the set scores, you can basically extrapolate this from the means. You can basically estimate each value based on this function. And you can do this with set scores, and you can convert these set scores then also into raw individual scores. So you can predict individual scores, not just sets, because you know the mean. And based on this mean, you essentially can use the mean to extrapolate it to individual scores. And this is what we will do today. Yeah, and you can do this just by rearranging the formula for the set score. So we know that the set score is calculated by x minus the mean of x divided by the standard deviation, right? Or the standard error, so to say, when we're talking about the distribution of the mean. And so once you have these given, you can calculate this back to basically get back on this level. And this we will do today on the example of stressful life events leading to depression. So I have posted in the module a spreadsheet that basically depicts exactly this data. So we have a spreadsheet. It's the same spreadsheet we had last time. So here's the correlation example. So now here we have individual 1 to 10 having a number of stressful life events ranging from 0 to 5. Bless you. Should we close the window? Is it cold? From 0 to 5, and they have an entry of the so-called back depression inventory. So you should have in the module also the original publication from Beck. That is actually one of the most commonly used surveys to assess for depression. And that's very common. So those of you who go into psychology will definitely hear and use the Beck depression inventory. And also those that go in medicine, that's quite common in all medical fields. So this quantifies the presence of a depression in, I believe, between 0 to 100. So these are rather low scores, but nevertheless, we may or may not see an association here. And this is what we're gonna assess. So the first aspect of this is always that you need to understand, okay, what data are we looking at? So we're quantifying central tendency, we're quantifying variability by quantifying the mean and the standard deviation, right? So we have done that quite frequently. So this is easy. We have a mean average of E2 to E11. Then we have a standard deviation, which is STDEF. Good. So this gives us the same starting situation that we have had. So we don't need to calculate it right now by hand. But this gives us the same starting condition as Noren and Heinzen have basically presented here. So notably, always make sure that you're looking at the same values. 1.6696633. 1.663. So they also use the division by the degrees of freedom. So they also consider the sample. So that's important for the distinction and making sure that you're using the same formula, not that you end up with different values later on. Okay, so we know the equation for the line that we want to quantify, and now let's go back to the Excel spreadsheet, because we have computed such a line already last time, and it's easy, right? So we want the number of stressful life events is the independent or dependent variable. Any guesses? What came first? The stressful life event or the? Yes. So the dependent variable is the BDI score, so the back depression inventory score, and the independent variable is the number of stressful life events. So the life events determine whether somebody feels depressed. So the easiest way to do a scatter plot, we know this already. This. So we essentially go and insert. We go and actually let's insert, and here's the chart symbol, and here we have scatter, which is scatter plot. So this is our scatter plot. So now it's easy. Now we just need to select these data points. We go and add chart element. We go on trend line. We go on linear. Then we select this trend line. Double click it. Form a trend line allows you here to select the solid line. Okay. And here on the bottom, you have display equation on chart and display R squared. And this is what we want to do today. So we are calculating, and this is the goal. The goal is to get to this equation. We want to get to this equation and to this number down there. So what does this mean? When we look at this equation, an equation has, and this is what this PowerPoint here showed. So we have in an equation, we have a predicted y hat. Notably, this is predicted already. So the hat indicates predicted y. Predicted y hat is predicted by an A and B that is multiplied with an individual x. So the A is our intercept. The B is our slope. Why is that? You remember that we had said that the intercept is where it crosses the x-axis, where x equals 0. If you want to use 0 for x, b multiplied by 0 becomes 0, irrespective of that is. So your predicted y hat will always be for x equals 0. Now, irrespective of that, so the intercept is of a battery. I hope I'm still audible. So now we have an intercept that is a constant. So no matter what this intercept is going to be, everything you're adding will basically be determined by x and your slope. So when you add here a 1 rather than an x, with x equals 0, and you use a 1, you get a slope that adds to your a. So that addition is going to be a constant. If you increase it with ones only, it will always increase by a certain amount that is constant. So this is how you get to your slope thing. We're going to calculate it backwards. We're going to get to that exactly that way. So the only thing we need to know now is a correlation coefficient, and we need a set x. That will allow us to quantify set y hat. You look skeptical.
Explain how you got the numbers from the charts, like to fill in the equation.
You mean these here?
Yeah. So how did you add numbers?
So you select this best fit line. When you select the fit line, there should be on the side a tab popping up that allows you to, so you can here change the shape of your function, and you can here pick display equation on chart, and you can pick display r squared value on chart. So the equation is exactly that regression function, and r squared is, we know the r squared already from the ANOVA, where it was between groups variability divided by within groups variability, determining the effect size of an ANOVA. So now regression and ANOVA are quite closely related. Not for this class, but in furthering statistical education, it will be closely related. So you essentially, with an r squared, you basically get the explanatory power of your regression function. So how good is your regression function explaining this scatter that you see? So the r squared is basically a modified, improved version of the correlation coefficient, where you only get a correlation between two variables. The r squared basically tells you, like, how good is my prediction? And were you able to reproduce? Okay. Everybody, what was this? Yeah. Good. Okay. Again, A is the intercept. Just think of x multiplied by b. When you put an x in there, when you put a 0 in for the x, b is gonna fall off. It's gonna be 0, and you basically have y hat equals a. So that's your intercept. If you're replacing now your x with a 1, you essentially get an access to that intercept. So that's like your movement from 0 to 1. So this is your slope. The definition of a slope is it's an increase in y with an increase in x. That slope can be negative, can be positive, but essentially it's always like y as a function of x. So you can calculate this, if you want to calculate it in a non-standardized way, you would calculate it by y2 minus y1 divided by x2 minus x1. That would get you to the slope. That's how you may have.
I remember doing this.
Yes. I know. That's you have done that in high school. I know.
It's the same thing, though, right? It's like the same thing.
That's the same thing. That's the same thing. Just right now we're facilitating that thing by using this just as a 1 and taking it from 0. You can do it more sophisticated.
Because when I learned the formulas, y equals mx plus b, I think it was switched.
Yeah.
But for this, it's y equals a plus bx. So it's the same formula, just swapped, but it means the same thing. Like the y-intercept is a.
Yes, per definition it's a. Yeah.
And the slope is b.
The slope is b. Yeah.
Okay, so it's the same thing. Just flip.
Yes, but that's it. Really, it doesn't matter what letter you use. So when I went to high school, it was K and D for the intercept.
So it was like bx plus a. And this then
Comes
A,
to-
it's the same thing, right?
Comes to something, yeah.
Okay.
You can use any random.
Yeah, I just wanted to make sure that.
No, no, none of the quizzes, certainly none of the quizzes. I went through all the questions, none of the questions would ask such an absurdity. No, it's just, this is a nomenclature thing, right? It's like you want to call it K, X, and D, it's like call it K, X, and D. It doesn't make a difference. Just the principle needs to be the same. But there is a nomenclature. I think it's a US standard to use A and B. I don't know. You probably know that better than I do.
And why was MX plus B? That's what I.
MX plus, okay.
But I went to college, so don't ask me.
No, I can't comment much. I didn't go to school here, so I can't comment much on how you learned it. No, but it doesn't really make a difference. It's really just that the equation presents in that form. That's all it is. And that you recognize that it is a linear equation. That is also quite important. Okay. Any questions with the equation, with the graphs? I think it's fairly easy so far, right? Okay. So now we want to do regression with the set scores. So now we are calculating the set score with the correlation coefficient to get to our set y hat, right? So if we just, let's do the screenshot thingy. Let's move this over to the Excel spreadsheet. Remember what we want to do. Okay, so we have a set y hat equals our correlation coefficient multiplied with a set x. So our set x needs to be calculated. So we're calculating this now by calculating x minus mx divided by SDX. What are we missing in the first place? Missing correlation coefficient. So I'm not going to spare you that. So we're going to calculate this quickly. So this is x minus mx. We do set minus mx. This is not set, x minus mx. So we are doing x minus mx. We need to log in mx. This gets us now to this. Now we're gonna do y minus my. This is the y minus the mean of y. Now we do x minus mx, so we can now also build. And this is x minus mx squared. This is basically just squaring this. This is our y minus my. What am I doing? Okay, we're doing y minus. Okay. We're doing a y. Sorry. Interesting. Okay, it's actually used that. That was weird. Okay. Okay. Okay, so we do a y minus my squared. which is basically now squaring this. These deviations. Now, essentially, based on that, we can now calculate the sum of squares. And good. So these are our sum of squares. So now essentially we need the product, which is x minus mx of the deviations only, not squaring it, y minus my. So this is now this multiplied by this. This is now the sum of this. And now our correlation coefficient should be the sum of this divided by the square root of this multiplied by this. That's obviously not correct. What happened here? Okay, so this is this. This is this. There's something out here. This minus this. This minus this. Okay. That's what gave me an error warning. Okay, so this. Okay. This minus this. This was not the problem. Okay, so it's this multiplied by this. Okay, so this is 0.58. So now we have the correlation coefficient of 0.58. My error was that I multiplied. I told you to not multiply the squares, but multiply the deviations only, which is x minus mx and y minus my. I multiplied the squares while I was saying don't do it. So, all right. So 0.58 is our correlation coefficient. We are now looking at set x. So we are calculating a set x that we want to quantify. So we want to quantify an x of 0, an x of y, an x of 2, an x of 3, right? So now our set of x is easily calculated by 0 minus the mean, which is 1.9, in a bracket, divided by our standard deviation, right? Minus 1.14. Please don't forget to log. Gotta log in the standard deviation as well as the mean. So this is now our set. Yep. So we are now looking at an x of 0, 1, 2, and 3. So these are stress for life events, right? So we have a 0, 1, 2, and 3. So 0, 1, 2, and 3 will have a corresponding set score, where the set score is calculated by x minus mx divided by the standard deviation of x. This gets us to our set score. Yep.
Why don't we do 4 and 5 also?
Before?
Like it's 0 and 2, why don't we do 4 and 5 also?
Oh, we can, but yes, yes, we can. As you just will see, we don't need it. And we don't need it because we only need 0 and 1 essentially. Because the only thing we want to do now is to calculate our intercept and our slope. And the intercept is easily calculated by calculating set y hat. All right, now let's get the other formula. So the set y hat is calculated based on, where's this equation? Where's this equation? Here. No. Yeah. R multiplied by xy multiplied by set x. So now the only thing we need to do to get our set y hat is to calculate our set x multiplied by the r. Oh, locking it in, obviously. This is G. So this is now our set y hat. How do we get now backwards? Because now we want the individual entry for y, right? We want the y hat. We don't want the set y hat, we want the y hat. And the y hat, because the set y hat is calculated in the same fashion as the set x, by x minus mean x divided by the standard deviation of x, the y is calculated the same way. So if you have a set y, you multiply it by the standard deviation and you add the mean, you have your y. You just rearrange it. So that's how you can calculate your y hat, your predicted y. That's pretty cool, right? So the only thing you need to do now is set y hat multiplied by your y, your standard deviation of y, which is here, $, plus your mean. So that's our predicted y hat. So this is based on your correlation coefficient. You're basically there to estimate your y using only your x entries. And now to your question, why didn't we calculate 4 and 5? We don't need them. The only thing we need is an intercept, which is where x equals 0. And we need a slope, which is essentially nothing else but y hat at 1 minus y hat at 0. And now we have confirmed that Excel knows what it's doing. It's considerably easy. It's like once the concept is clear, it's considerably easy to do these calculations. It's not terribly hard. The concept is just tricky because this relationship between set y hat and set x with the correlation coefficient permitted via the correlation coefficient. This is really where the money is. Yep. The CY hat is the product of the correlation coefficient with the set x. That's our R. So the R is the product. No, it's actually the quotient. It's so we're taking the product and the sum of products between x minus mx multiplied by y minus my. This sum, which is 80.7, divided by the square root of sum of squares x and sum of square y. It's this formula, right? This is the previous class. This is the correlation coefficient. The product of x minus mx, y minus my. Summing that up, dividing it by the square root of the sum of squares x and sum of squares y. So this relationship between set x and set y hat, permitted by the correlation coefficient, this is the concept. Because the correlation coefficient gives you direction and the positioning within the coordinate system with slope. Okay, so now we have intercept and slope. So what do we know based on that? We know that with each stressful life event, your back depression inventory score will increase by 3.24. And when you have no stressful life event had ever in your life, your back depression inventory score is 9.542 at that age and that population of 10. So 9.5, intercept, slope 3.24. Any questions? No? So what do we want to do now? So, okay, so now we have a model. We have developed our first regression model. So we know now that we can predict the y using our x based on this population of 10. Now you want to do, how good is my model? And we talked about the R squared. We have it already here on the chart, but we also want to calculate it. And the calculation is, how much better is our model than just using the mean? The mean of back depression inventory score is 15.7. Is our model really better? Let's find out. So the way you find that out is by comparing this essentially to your prediction. So your prediction will be, let's actually go here. It's not as the correlation coefficient. So now we have a y hat. We know now that our y hat is estimated by the number of stressful life events. So we have an intercept of 9.5 plus, because it's a positive slope, plus 3.24 multiplied by the number of stressful life events, which is for the first individual one stressful life event. What did I do now? Oh. So now we want to lock this in, our slope and our intercept. So we get, for the first individual, we get a value of 12.783. If we go all the way down, we're getting estimates with this individual number 9 getting the highest BDI score of 25.75. So now, what we want to find out now is the reduction in the error. So we're calculating now
y hat minus y bar. So y hat minus y bar is the deviation of our estimate from the mean. So we're getting y hat minus y bar. Y bar is here. So the deviation is 2.9 for the first individual. And then it varies. So that's the deviation of our estimate. Squaring this up is easy. So what we are getting now is sum of squares of the error. So we have a sum of square of the actual estimate, which is here y minus my squared. This is our sum of square y. And then we have a sum of square error. So this is now sum of square y. The sum of square error is, let's sum this up here. And our sum of square error is 261. What do we see just by the naked eye? It's gotten better, right? And our R square is now the sum of square error divided by the sum of square y. So how much better is our estimate compared to just taking the mean for the entire population? How much better is our estimate, our prediction, using that function as compared to the mean? Yes. Okay, y hat is the intercept plus the slope multiplied by the number of stressful life events for each individual. So it's intercept plus slope multiplied by B2 to B10. And you're building this row. And then you're subtracting your estimate. And you're subtracting your y, your my, your mean of y, from your individual estimate. You're squaring this and you're summing it up, and you're basically getting to your sum of square error. And dividing those two will allow for you to see how much better is the model as compared to just taking the mean for the population. It's a powerful marker, right? Because that gives you really an insight of how much accuracy does my model have. Now imagine this with 10 more variables, where you take age into account, you take, I don't know, socioeconomic factors into account of those children, you take performance in school, you take all kinds of different dimensions you take into account. And you basically, you are predicting for each individual was quite high, was a quite high certainty what this BDI score could be, if you know what determines the BDI score. And this comes back to my point with the correlation, is like you need to understand all unknown unknowns to quantify and build a model where you really have causality involved and you really understand what you're predicting. Okay. Any questions? Yeah.
So what is the sum of squares in the last column called?
The left column, this one?
Like the, yeah, what's the sum of squares called?
Sum of squares error. As sum of square error. So that's the estimated y hat minus the mean y. And to visualize this, and that's actually pretty, I gotta give it to Norton and Heinz, and sometimes they really have absolutely fabulous graphs. There's line of best fit, standard error, line of best fit, regression, coefficient of determination. This is what you're comparing. So this is our error. This is if you just take the mean, because now you have this these deviations, right? And we have quantified that for the standard deviation. So these deviations are the deviations from just taking the mean of 15.9. If you're now comparing it to your regression sum of squares error, you basically get something which is here the prediction for each value, which is your line. And you get the difference between the individual data point and your line. And this is called the so-called residual. It's a residual from your regression estimate. And this residual is extremely important for all regression methods that you will be employing later on. For example, it's extremely important for all regression models that there's no difference between the residuals in the lower values compared to the residuals in the higher values. So this is called homoscedasticity. And you may remember the term from ANOVA, where we essentially had homoscedasticity as one of the requirements and assumptions for the ANOVA. Any questions so far? All right, we just built our first model. Okay. So this goes in the same direction, right? So when you are estimating the standard error of a prediction, these residuals determine your explanatory power of your regression function, of your regression model. The larger these residuals are, the smaller your explanatory power, the lower your R square, your coefficient of determination. Or also called the proportional reduction in error, R squared. All right, we did this, we did this, we did this, we did this. Regression to the mean. So since everything is based by using the mean, extreme scores have a tendency over time to become less extreme because they gravitate towards the mean. When they do so, they become actually a problem. Because outliers, due to one extent, they will shift your regression function because the mean and the estimate of the slope is quite sensitive to these outliers. But the center will always be around the mean. So from that end, outliers in extreme values tend to really shift your slopes and change your slopes. This is why regression sometimes can be a little tricky when you have outliers. This is why one of the #1 assumptions that need to be met in regression is normal distribution, which makes it limited. So the limitations are the same essentially with correlations. Since it's often not from true experiments, randomizations, which is not really true, you would use regression models in randomized trials as well, in a different way. But it is a limitation that you need to understand that this is not a causal relationship, it's a correlational relationship. And for a causal relationship, you need randomized settings. Only then you can draw conclusion on causality. The independent variable is in univariate regression, it's a scale variable. And limitations in predictions like those found in correlations do apply, which is essentially a normal distribution, homoscedasticity, and that random selection of your participants. And back to the regression to the mean, extreme scores will always gravitate towards the mean. And this is particularly true when you look at something that is called a time series. And we have seen a time series plot when it came to visual displays of data. Well, basically, here in this context, in this time series that they're meaning to present here, what they mean to show is that everything that was extreme will bounce back to what is a mean. That means that extreme values are not staying extreme forever. They may come back to their mean, which is which is a problem if you build regression models, for example, of the stock market, and this is what they use in the stock market, because you gotta be aware that all models that the stock market that are used to predict the stock market that are essentially built on historic data, right? And you have a problem predicting the future using historic data. So this is why their thinking was going in the direction of stock market. And essentially, when you hear statisticians working on the stock market and predicting stock fluctuations and volatility, all they're doing is regression, essentially. Well, they do more sophisticated things, but essentially it is a form of regression that they're doing in many cases. So this is the regression to the mean. Extreme outliers tend to go back to the mean over time. Any questions on that? Because now we're touching on the last topic, and this is where we're gonna end today. We're gonna talk about multiple regression. So as I said, so the R squared essentially is the proportional reduction error. So this is essentially how much explanatory power does your model have and can explain from your scatter. So when you have, and the example between stressful life events and the BDI score, the depression inventory score, essentially is an example where you already can fathom that there are different factors that's coming into play. It's not just stressful life events that determine depression, right? It's more than that in many cases. One way to deal with that is by including additional variables into your model. There can be anything virtually that you think is causally related with depression. Arithmetically, statistically, when you include additional covariates, you will always see an increase in your R square arithmetically, because essentially as soon as you have more, you explain more of your variability. For that very reason, you distinguish between an R square and an adjusted R square. An adjusted R squared, you will see that just on the next slide, no, not on the next slide, on this slide, no, also not on this slide. So essentially, an adjusted R square is an R squared that is being penalized for inclusion of additional variables. So you're reducing that R square estimate according to the number of covariates you include in your model. And this is super important when you have multiple variables, because you can include, depending on how many variables you have of your participants, you can include all the variables you have and you get a higher R square arithmetically, but you should not base assumptions on an R square that is artificially inflated just by including just by arithmetic principles. So this adjustment is extremely important, particularly when you have small sample sizes and a large number of covariates. So, but this is actually not part of this. But this just, it's important to keep that in mind, that there's an adjusted R square and a standardized R square or a standard R square. What we have here is a software output for regression, which is of my most favorite software, SPSS. We will see some on Wednesday, doing this in R. What you see here is, so you see the model parameters that were included. You see the constant, which is the intercept. You see life events as one covariate, and you see sleep problems as a second covariate, because other factors determine depression. One of them is sleep problems. You have here unstandardized coefficients and standardized coefficients. We talked about standardized coefficients. These are our ZY heads. Then we have unstandardized coefficients, which are here our B's or betas. So what's interesting to see, you remember that we had an intercept of 9.5, I believe it was. Once you include sleep problems, your intercept is -4, which indicates that a certain part of your depression of that population was caused by sleep problems, because including the sleep problems, suddenly these 9.5 are disappearing, meaning that you can be depressed without having life events that are stressful. So this essentially comes from sleep problems. And we've all been there, right? It's like you have stress in your life, you still don't sleep well, and that makes you depressed in the long run. Then you have a standard error, which is determined by the residuals over the entire range of your data. And these residuals will get you to a T. And I would like for you to pay attention to the T, because again, we're looking at normal distribution. And this T essentially leads you then to determine whether these predictors are significant in your model or not. Which sleep problems are actually significant and the life events are not. Which is also, again, coming back to correlation is not causation. Coming to the conclusion that actually, this actually has more weight in your prediction than your life events. Which is interesting to see, right? And lastly, any questions to multiple regression? So this definitely will be in the quiz. I'm just flagging this. So there are a couple of multivariable regression outputs that will need to be interpreted on Wednesday and for the finals. Notably, not only those of Nolan and Heinz. There may be some I made myself. Okay, multiple regression, everyday life. So as I mentioned, this is a very powerful technique. It's a very common technique, very popular. You can do a lot with that. So you basically have apps and websites. When Instagram tells you that you want to buy the newest electronic gadget, this is a regression model going through your shopping behavior. It's forecasting. It's forecasting what you want to buy. It's forecasting what you will buy. It's forecasting what Amazon has to ship to the warehouses to get it to you in prime within a day. Anticipatory shipping and shopping. Yeah, that's it. So all these algorithms that you're exposed to, you don't see any, but they know you. They know you better than you know yourself in many cases. It's interesting because essentially what you can do, you're not only seeing, okay, this individual bought that and bought that 6 months later. No, they know patterns. They know patterns that you're not even aware. Your Instagram or your social media or whatever you do, this is the perfect example. It's like it will tailor the posts you're seeing. It's influencers buying data from, so it's an whole industry. And this is all some form of regression in some shape or form, it's statistic behind it. And yeah, this is where we'll end today. If no questions, we can conclude for today.
Thank you.
In my strategy class, Uber, that company,